My name is David Gustavsson. I'm the VP of Engineering for XIO. Been a part of this project since it kicked off very early on. And we're going to cover, keeps going forward, business velocity and software-defined data center. Talk a little bit about what's changing and why does it matter? And how does hardware have to react and change with it to, frankly, be relevant? There's a lot of hardware out there that's being discussed out of relevance today because you put a software-defined something in front of something and then it becomes not about hardware. Hardware still matters, but let's talk a little bit about what's changing first. So there's an interesting phenomena about the last 5 years, probably longer than that actually, but it's a trend that's going on regarding who is making a lot of the decisions. So this is what we are seeing, what we are identifying as a big shift in IT and what's going on that drives a very, very different thinking and a very different dialogue that is also now driving a lot of different technology investment and development. So I'm going to take you through a little bit of a scenario here, and hopefully it makes it to the camera okay. So what we've seen in IT many times, right, is the IT team itself with its leader is actually telling the line of business guys, CEO, business owners or so, how technology can accelerate their business. And they are the innovators. They are driving why it's changing. A lot of that stuff, frankly, has become second-hand knowledge. Everybody who is worth their salt in the line of business today knows what they need from IT just as much, if not the opposite. So what's happening is here, the line of business guys, right, are starting to drive a lot of give me, give me, give me to IT. And everybody is trying to get the job done, but lower and lower budgets. And concerns about all kinds of different risks that they have been now told to manage, right? So inside of the IT team, what we have is networking, we have storage, we have servers, applications, of course, we have databases. Usually they are separated. We have desktops and help desk pieces. Clearly, different size organizations have different type of organizations inside of IT, but these are kind of the main responsibility areas inside of it. And for large organizations, they have entire teams doing one particular thing, and the reason for it is because these areas are complicated, especially in a large scale. You can spend an entire lifetime trying to dig in and understand everything in one area, and you still won't, right? So a lot of time is spent creating a career with your expertise in a particular area. So the networking guys' key objective is keep the intruders out. Naturally risk-averse philosophy, that's the whole point. The storage guy's objective is never lose the data. Naturally risk-averse, right? Server app guys is provide applications and services for the organizations that need them. So different objectives for different people inside of here. But what's happened over many of the years is that the risk-averse philosophy has driven what I would call a no-oriented organization, where it's easier for the tech-savvy IT guys to explain to the business owners why they can't get what they ask for, right? And what the risks are. And if you now have a no-oriented organization, it becomes static, it becomes safe, and you're frankly not pushing the boundary, right? So what's going on out there today? Well, it's changed. There's companies out there that have started with the philosophy of saying yes, no matter what it is. So now, all of a sudden, you have people over here screaming from the rooftops, I'll do it for you. It's a yes. Cloud providers through the wazoo. Different type of services, different type of pieces. So the line of business owners here are now start looking at whatever cloud opportunity and cloud providers out there. And frankly, I don't know of a cloud provider that says no today, right? They just need everything. So they say, come, I'll give you what you need. Doesn't matter if they frankly can do it or not, but what's happening now is these guys are looking at their stuff and saying, hey guys, I'm not getting what I need from you. Pretty straightforward. I gotta go to somebody who gives me what I need. Well, it doesn't really bode well for the internal IT organization. So what happens? This first cycle is these guys spend a tremendous amount of time convincing these guys that this is dangerous and it's unsecure and they're gonna regret it. Cloud is not a real option, right? Because cloud is not under my control. Once they go and dip their toes in the water and say, hey, you know what? There's actually useful ancillary services that I can offload that has low risk. Office 365, other type of things that might have less security concerns from a business perspective. They keep the golden bits and the tier 1 database still in-house, but they start going outside. They realize this is actually working, so what happens? These guys are starting to realize, you know what? We got to figure out how to provide the same services that the cloud guys are doing internally for the line of business guys to keep our job, for us to actually also become a viable business and drive progressive applications and development, right? So, at the same time, there's been an interesting technology revolution inside of the IT organization that has shaped the mindset.
David?
Yes, sir.
Not to be rude, but
please.
We understand the problem. We work in those dynamic IT organizations.
Please, that's perfect.
Could we move on to?
I think you were quite good there. You went longer than I thought you would.
Thank you. No, that's fine. The point I'm trying to make here is it's changed where
we understand.
These guys
we understood for months.
Fantastic. So this makes a big difference for us because while as a storage vendor, these guys have been what matters now is figuring out how to virtualize the data center, right? Provide what needs for the virtualized data center, and that changes everything as a storage vendor. And it also changes what type of device and what type of integration you need to provide to participate. So, in this type of an architecture, in this type of a dynamic scenario, what matters is what the virtual admin and what the virtual architect needs to succeed in the software-defined architecture, right? So, like we talked about earlier, it's not about being a storage expert anymore. It's not about protecting your domain. And I want to be able to manage those storage resources just like I do my compute resources, right? Storage management and how that has been done, because of its unpredictability and how it works, has been very, very, very black art in most ways. And many times it's also very vendor specific, that you manage a particular storage array a certain way and another one a very, very different way. And what matters to these guys is not the storage actually. It is, can I get the job done? So, how does it perform in a particular use case? VDI, recompose architecture, will it survive a boot storm and actually provide for the new VDI instances in its new configuration fast enough without impacting my end user space, right? This lays the foundation, if you will, for a very, very different philosophy in building storage. But a lot of storage has been built what I call bottoms-up philosophy. You take the disk, you do the pieces, and then you take a bottoms-up architecture. It's about flipping that. It's about figuring out how you fit into a much, much more integrated ecosystem to make storage automated and resilient and fast such that you don't have to worry about it. Okay, questions? Very good. So let's dig in a little bit on technology. Here is our box. This is the ISE, our product today. We're going to dig in a little bit about, take a look at what it is and how it does things and how it achieves certain things. So, in effect, a 3U box containing up to 40 devices, SSDs and HDD mixed. Everything is a dual redundant architecture with an active controller architecture. So every data path is available on any port, meaning every volume can be accessed through any active path as well. Take a look a little bit on this. Inside of here we have 2 data packs. These data packs are sealed. They are not built to replace drives. They are meant to be unified and optimized for drive environmentals, meaning if you do mechanical engineering, optimizing for the drives, having the best possible environment that they can live in, they last longer and they perform better. It's very simple. While a lot of traditional architecture and what drove the philosophy of design was make it easy to replace them. And when you make it easy to replace them, well, you take away the tools, you make plastic sliders, and you make small little latches that makes, frankly, compromises the vibrational environment tremendously. What we also do is, as we do a dual redundant architecture with our controllers, those controllers have mirrored write back cache, what that allows us to do is to decouple a lot of the front-end IOs to the back-end IOs on the drives. That's a tremendous important thing for us to be able to give you the predictability and the performance we talked about. As we use DRAM as a cache, we have to have an internal battery or power supply backup such that we have, in case of a power failure, we still have data integrity. So in these scenarios, we are using supercapacitors. This is leveraging some of the development in capacitor technology that comes from the regenerative braking in hybrid cars and such. So what this allows us to do is charge up a bank of capacitors to leave the system running for a certain amount of time after it loses power, such that we can safely destage memory into a non-volatile stage such that you never lose the data in that sense.
So how long do these capacitors last?
So those capacitors allow the system to run for about 8-9 minutes or so.
How often do they need to be serviced or replaced?
Which ones?
The capacitor.
The capacitors. So this is the second generation power source in the IEC technology, while the first one was using lead acid batteries. And lead acid batteries, especially with environmental control, logistics and shipping and charging, frankly becomes a nightmare. So this is the second generation, and the reason we use supercapacitors is because they're actually maintenance free. We don't have to maintain them at all. They charge, they discharge. One of the tests that we did for this was to try to do an extreme performance test by inverting the polarity of the supercapacitors, charging them, overcharging them for 2 years, and we had a blast shield sitting on it over in the lab to make sure that nothing would go bad, and it's still running 4 years later. So at this point we have no indications that the supercapacitors are actually needing any maintenance. The lead acid did, frankly. That was one of those things that so what happened when the first generation of ICE was, while the drive replacement is almost always the most replaced part in a storage architecture, right? We eliminated that, and the battery became the second most replaced part instead, right? So that's what we attract now with the second generation, if you will, architecture.
How disruptive is it to replace one of these, the capacitors?
So the capacitors are online hot swaps. You pull one out, it's architected to run the entire system. Should one capacitor unit not function, the other one will keep the system running fully redundant for 8 minutes, right? And the whole idea here is also engineering for margins, meaning the problem with, in certain use cases I should say, the problem is actually not how many minutes you have left of energy, it is the temperature profile of the core of the CPU, because when you lose power, you lose fans. So you need to be able to maintain the CPU core temperatures within the limits that you need, even in the scenario, worst case scenario, you lost your AC in the data center, you lost your power, and now you're running for a long time dumping cache, if you will, and what happens is that the core temperature goes up and you will be toast. So we do a tremendous amount of extreme temperature testing and make sure that you know, even in a 130 degree data center, it has the time to get it done.
Yeah.
You know, the drive component didn't look like there was enough shock absorption to deal with rotational vibration and stuff like that. You think it's adequate there, I mean, especially a second row and stuff like that?
Great question. Not only do we think so, we know so. So what we do is we work with Seagate, and Seagate has, as you guys know, we used to be Seagate, right? So we have a lot of access to information and contacts, and we work with them hand in hand in developing those enclosures. And the way we leverage them and their knowledge is also specific tools that are accelerometers mounted on the drives, and we profile the vibration profile on each drive slot, and we then do vibration testing, and by doing that we can actually identify if there's potential harmonics or fan crosstalk or any type of frequencies that are, if you will, having an impact.
Well, you guys used to have, the pack used to have counter-rotating drives as well. I see that's not the case anymore.
Correct. And this goes back from testing and measuring, right? So certain design objectives is, all you do is try to keep a certain rotational vibration low over a certain frequency range. And Seagate has very, very clear specifications on how where the drive is sensitive, right? The micromechanical closed loop feedback is very, very sensitive, for instance, at about 2500 or so hertz. And you got to keep those frequencies incredibly low. So by understanding those frequency profiles, we can then mechanically engineer the optimal architecture for that in closed loop with Seagate. Actually, we ran some tests at full speed, full I/O, sent the results to Seagate, and Seagate says, great, now turn on the system and run it. Right? They thought it was running idle, because that's usually what they compare against, right? Because of the vibration profile, it was such that, yeah, it's a completely different world than comparing to a traditional JBOD with replaceable sliders, if you will, because the whole idea is to optimize for it.
So wouldn't that change per drive type though? So as you get a new drive, you have to go through that whole process again?
Yes and no. So frequency of response in mechanical vibration has to do with stiffness, harmonics, dampening, right? So we use 10K RPM drives, and IS-1 used 15K and also the 7200, right? But we have standardized pretty much at 10K RPM drives. And the reason for it is, frankly, is because we get the performance way above the 15K drives, and we get the capacity and the economy from the 10K drive, and also the power efficiency. So it's the sweet spot, if you will, of all these intersecting parameters that gives us the best thing. So when you have a 10K drive, you need to worry about the 10K harmonics because it's a particular rotational piece, right? So you can create a generic design that is very broad, and then to your point though, you got to verify every drive model to make sure that you don't have any kind of surprises or nasty harmonics or so.
So what happens if you just have one drive fail? Just
Great
one.
question. We're going to get into that.
Take the whole thing.
Before, because that's a whole other thing that they're going to talk about here. Can we backtrack for a second?
Yes.
About you said operational temperature. You guys do testing, heating these things. Do you ever cool them down?
Yes. And we
What's
have had
the
some
minimum?
interesting anecdotes where performance on the drive
Minnesota or something.
Yeah,
had a stair step. No, absolutely. So performance of the drives are also actually affected by temperature, and sometimes it's actually by pure bugs. We had a scenario where we were cooling down the system, and I think it was between 12 and 18 degrees Celsius, we saw a stair step function in dramatic loss of performance. Right, so then we work with the Seagate guys and try to figure out what's going on with the potential impact of performance and test drives, right? So early on in qualification cycle, we work back and forth and then identify those pieces. So yes, we have temperature chambers and that we take these things through. So both ways, cool and hot. And that's also another aspect of lead acid that is not very good, frankly, because as lead acid drops in temperature, it loses a lot of its energy carrying capacity, right? So eliminating some of those pieces with supercapacitors is also a nice thing, if you will.
You know that about starting your car
obviously-
in Wisconsin, right?
It's a
Being
chemical
Seagate.
reaction.
Yes,
You get access to that information.
correct.
Does that now not limit you though to being only one vendor?
Yes.
There are only
Fine.
2 vendors.
Yes, no, but single source. So when we came up with this 7 years ago or so, that was actually a pretty big industry concern, right? As single source vendor, how are you going to manage that? Why is that a problem? You know, because most of the vendors out there at least do a dual source such that they can do a price negotiation, right? It's a fantastically useful tool from a price negotiation.
Or a country gets flooded or something like that. You know?
Turns out everybody was affected by
Everybody
that
was
too.
affected
So
by that one, but I'm using
that's
that
the
as an
problem
example.
of the industry today. It is such a centralized and consolidated industry anyway, so that's not really that big of a difference. Now, by picking one vendor and working closely with them, what we can do on the other hand, we believe brings more value to us than what second sourcing would do. By integrating, understanding their dynamics, by profiling their particular drive models, and also by working with them and they providing our particular or firmware capabilities in those devices, we can now integrate with the drive, not just use the drive, right? While a lot of storage vendors integrates to the SCSI spec, read, write, whatever, right? We do a lot more, and we're going to go into some details around that later on and why we do that. So another thing that we do, of course, carrying the data. So here are our controllers, if you will. So we do all our hardware design in-house, all our software design in-house. Everything is written from scratch, drawn from scratch. It's not a compiled pile of open source pieces that hopefully works. It's everything from scratch. This architecture is x86-based architecture, PCI Express data path carrying architecture. So think of it as a motherboard. Server motherboard with SAS HBA on the back end and a Fibre Channel HBA on the front end, if you will, and integrated switching circuitry, yes.
So you're not running Linux on this?
We are running Linux, but we only run Linux as an operating environment. We're not relying on Linux as a data path at all.
Okay.
From the bit hits the front end to the bit hits the disk, Linux is not involved. We run firmware processes that we have built ourselves to manage the entire data path, right? And the reason for it, frankly, is because, well, we need to make sure it stands up to our standards. How should I put this? We take advantage of some of the hardware architecture benefits that we do in ways that traditional servers have yet to reach. I believe they might get to at some point, but are not yet. Like, for instance, we tie these controllers together with a PCI Express bus via a non-transparent bridge, such that each side has memory mapped via PCI Express the other guy's memory. So every bit that comes in on one side gets mirrored over to the other side immediately and are bi-directionally accessed by memory, if you will. Yes, sir.
I have a quick question about the disks. So you rely on Seagate, but what happens if Seagate stops to build disks, like a few years ago with a flood or whatever? So
the flood actually did impact us. And what happened on the flood was it impacted everybody, frankly. Not just us, but also EMC, HP, and everybody else, right? So what happens if they stop making disks? Our business assessment of that is, by the time that happens, we have also stopped using disk. That's kind of the point of it, right? Because the frank answer here is, I believe the relationship that we have with Seagate.
But it's not a question. So
well, it's a long way around to saying that they're screwed if they stop making disks.
Well, no.
So,
Or they have to use something different.
Frankly, I don't. Yeah. If they stop making disks today, we would have to swap horses, integrate with somebody else, and maybe we would integrate to a lesser degree or so. But yes, it would not be the same relationship that we have with Seagate today. Our heritage is with Seagate, no doubt about it, right?
Yeah, and given the fact that there are really only two disk vendors, relying on one of them isn't that different than saying we can use disks from either Seagate or Western Digital. Yeah, the industry's consolidated to the point where it kind of doesn't matter.
One thing you may have noticed,
it's kind of like
the SSDs aren't actually Seagate SSDs.
Yeah, we noticed that.
No, they also don't vibrate.
I noticed that.
Yeah.
But we're going to visit them later.
Good.
Very
Glad
good.
you noticed that.
Very
the other
good.
thing I've noticed is that Chris is slowly building an ice over there.
Yeah, I can't. I'm just working out. I've got one of the screwdrivers to take that out.
Just keep
I
an
think
eye
I've
on the
got
chassis.
something actually.
So,
Luckily, it won't fit in his carry-on.
Yeah.
You mentioned the
That's
Fibre
what you
Channel
think.
HBA. Is it all Fibre Channel or?
Great question.
So, different architecture for different generations of product, if you will. That controller right there. So first generation IC, yes, it was Fibre Channel because the disks were Fibre Channel and HBA on the back end, right? Fibre Channel on the front end. Well, as enterprise drives has moved over to SAS, the back end has moved to SAS, of course, and now it's all SAS integrated instead of Fibre Channel in the back end. On the front end, on the other hand, it was still providing Fibre Channel on the front end. Now, this last general available product as of this month is iSCSI on the front end. So it's 40 gig, dual port 40 gig Ethernet per controller. So it's 40 gig Ethernet front end, if you will. So no Fibre Channel at all on that generation, if you will.
So do you run FCOE on the?
Oh God.
So we do play in FCOE on the Fibre Channel side. So when we hook up to a Nexus 5596 or so, 48,
Yeah, but
we become a Fibre Channel target.
That's you still doing Fibre Channel. That's
Correct.
Not you doing
Correct.
FCOE.
No. Correct. Exactly. So it's iSCSI.
So you're moving from Fibre Channel to iSCSI.
Correct. We are opportunity.
Both.
We are, exactly. We are supplying both, if you will. What we're seeing is there are cloud vendors out there that has gone to an Ethernet-only architecture that has a need for what I would call Fibre Channel-like infrastructure reliability and performance. They don't know it quite yet that it's hard to get there on Ethernet. And what we're building with this box is the ability to carry iSCSI into that space.
Okay.
Make sense?
Oh yeah.
Yes,
we
sir.
never got back to Pumala's question
Yeah,
about
I was
the replaceability of the.
And we're going to get there.
backpacks.
So it's actually later on in my presentation. I apologize.
Sorry if I jumped the gun
No,
there.
no, no, it's all good. It's all good.
Yeah, I was
Perfect.
just worried that.
I'd rather have it
we'd
interactive. I
slip
like it
past and
interactive.
not- Yeah, because it's cool.
Yeah.
The controller boots from this SATA DOM?
Correct. So it's dual redundant. So both controllers has their own SATA pieces, and they do also use that for the cache dump, if you will, right? So when you lose power, it moves the data into that.
So can you just go back and you mentioned PCI Express. Did you say that you were extending the PCI Express bus between the two controllers?
Correct.
Right.
So they connect via a backplane, and those PCI Express lanes allow me now to memory map from each controller the other guy's cache. So I can use his cache, or he can use my cache, if you will.
Latency on that?
Latency on the PCI Express?
Nanoseconds, 10
no, it's not nanoseconds. It's, oh, geez, 1.3 microseconds?
Okay.
1.3 microseconds.
And what's the options for expanding that? So if you decided to build a scale-out technology?
So what we do is we have what we call a tightly coupled cluster between these two controllers, right? But then we also have a loosely coupled cluster architecture that I'm going to get into a little bit.
Fair enough.
And that has to do with utilizing the front-end data path to tie two boxes together to collaborate to serve storage, such that it becomes a storage cluster, if you will.
But you could do that at the back end if you extended the PCI Express bus out the back of a...
Yes, there are ways to take advantage of a low latency, high bandwidth bus for that purpose as well. And for us, it wouldn't make much difference. The only reason is the front-end connectivity is what customers use to cluster these together today. So we would have to expand, if you will, the box connectivity in a proprietary way. So
David, so you actually have an 8 gig Fibre Channel version of this as well as the 40 gig.
Yes, yes. So 8 gigs or 4 40 gigs is what we do. So inside of this is pretty straightforward. x86, SAS initiator, SAS expander network on the back end. Each drive has dual port connectivity. So in essence, we have 80 SAS connectivity points on the back end. So quite a bit of high-speed traffic and high-speed lanes. But the beauty of integrating everything in one package like this is it becomes incredibly predictable. There are no miswirings. There are no varying environmentals. And we can hone down simple things like signal and high-speed patterns incredibly tight, such that we know we have a high-quality information path, and there are no variability to it. And the no variability plays very, very important when you talk about avoiding service issues. So you can look at this one as well if you will, I guess. Okay. Very good. So that kind of takes you through a little bit of the basics of the system. So what do we get out of this, and what's the point? The whole point is to optimize media. Give the opportunity for the drive to behave the way it can. The drive are capable of a lot more than what actually drives are used and see being utilized in a lot of systems. A lot of best practices, guidelines for performance scoping and architecting in the industry are relying to these numbers. If you look at the lower left corner here, 7 and 2Ks, 10Ks, 15K spindles, 85 to 100 IOPS, 125 to 150 or so. Our 10K spindles are routinely running between 300 and 400 IOPS. And the reason we can do that has to do with how we use them. It goes back to, again, decoupling the front-end I/O pattern to the back-end I/O pattern in a way that you can optimize the I/O pattern to give the disk the opportunity to optimize itself, but also to minimize seeks. So part of what this mirroring bus allows us to do is that we can now share a lot more intimately the information between the two controllers about how we use the drives, such that we can do a distributed seek manager. So when you have two controllers talking to the same drive and they don't know about each other, they stomp over each other and it ruins the performance completely. Now, if you on the other hand share the information and you allow these to order the IOs in a way that is optimal for the drive across both controllers, then what happens is that the drive can perform a lot better and does not get disrupted. It's the same thing as when you do something, you focus on one task and you don't get interrupted by other people. Same thing, and it pays back big time. A lot of the pieces we talked about early on was the environmental conditions, and some people kind of don't really take the environmental seriously. I don't know if you guys remember, it was a long time ago, it was a YouTube viral thing where a guy ran into a data center and screamed into a JBOD and the performance dropped off.
Yeah.
Brendan Gregg.
Done one.
I saw that myself and thinking, oh, I gotta try that. I ran into the data center, started screaming. Turns out the front desk lady thought somebody was stuck on the roof. So she tried to go, but anyway, couldn't get it to work. Couldn't see any difference or so. But really what it came down to is that spurred us a thought, okay, so how do we test this? What's really the practical exposure to this? So what we do also is we take a fire alarm and we take it right next to the ISCs, and we actually measure the frequency response on the different spots during that fire alarm exposure. And fire alarms are, by OSHA regulations, not allowed to go in higher than 120 decibels, but they have a very, very nasty frequency response and to make your ears sensitive for it, right? But what it does for it, just the sonic vibrations alone from that guy yelling into JBOD drop performance. And the reason for it is because the micromechanical seek loop inside of the drive was missing tracks. It wasn't finding the track to read for, so he's spinning and he has to do rereads and rereads, right? And it seems like an extreme example. Turns out it's actually not that extreme, especially not if you have designed an enclosure that are very, very close to the tolerances that Seagate tells you that you should do. So just by doing a good mechanical design, you actually gain performance, believe it or not.
That's a point much underestimated
Hugely.
by storage folks.
Hugely.
That the mechanic, when you start talking about we start talking about server SAN kind of things, the degree of mechanical engineering matters a lot more than people think.
And also a lot of people think it just really affects reliability rather than performance and predictable performance. It's the unpredictability of it that we're smoothing out.
And on top of that, also what happens in some system architectures is, we call it the bad administrator problem. One drive falls behind, and that one drive drags everything else down. So you have one bad apple in the cart, and it makes everything else spoiled. And when you have an architecture of distributing data in that codependent of a manner, then what happens is that you do not run any faster than the lowest contributing factor, if you will.
I know I've seen that, where one drive wasn't properly seated.
Yep.
And
took out everything.
Well, that's actually the nature of the firmware differences often between a consumer drive and an enterprise drive. The timeouts, at which point you stop, you abandon the drive that's dragging you down. Like
time-limited error recovery.
Yeah.
And usually what happens is those events are so painful that it drives a philosophy of design and design objective in the firmware team that says, when there's ever a problem, let's throw the drive out, because when the drive is behaving badly, we can't deal with it. It is such a big blast radius, as I call it, right? That we just can't deal with it. So let's be very aggressive and get the drive out of there, because if we're not, we're going to have problems.
Right.
And that has very foundational
the array
ripple effects.
And the array controller marks the drive bad, and you send it back to Seagate or Western Digital, and
you'll see
it goes in the no problem found pile.
Bingo. Exactly right.
Next slide.
So, predictability. We talked about predictability. Predictability comes with design margin. It comes with understanding the environment and when you do trade-offs. So first of all, our performance claims are always at full capacity testing. We don't do the whole 15% utilization and say that it's 2 million IOPS and say, hey, this is an awesome thing. We expect, the best way I can know how to explain the personality profile of what we have tried to build is that it is a workhorse. It is meant to be loaded full, and it's meant to be loaded at full performance at all times. It is that tier one backbone of your infrastructure that is just meant to sit there, hum, and it's pretty unglamorous, frankly, right? That's the point. Focus on the fundamentals, make them better, okay? Comes back to, again, how do you then also ensure in a multi-tenant architecture, meaning you have many, many different servers talking to the same storage. A shared storage architecture, sometimes what you end up in resource starvation, where one server gets more attention, so to speak, than another one, right? And you don't get that fair. So we have adaptive fairness algorithms on our front end to separate resources internally to make sure that all servers talking to us get their adequate resources and in a fair manner, such that we don't get noisy neighbor taking down the entire scenario, if you will. So it's a naturally QoS-oriented architecture from day one. And so let's see here. Flash then. So we have the pleasure to work with some real experienced people in the industry. I don't know how many of you guys know Richard Larry. Steve Sicola is one of them, founder, visionary, set this in motion. Richie Larry is another guy that we work with. He came up with this idea, you know what, the way guys are using SSDs today is like plop out the old drive, slap the SSD in there, and run with it, right? And as you guys remember, 4 or 5 years ago, everybody realized, oh, the SSDs are much, much faster than any controller can ever handle. So now we have a new generation of flash player coming to market to eliminate that bottleneck, right? So they created a flash-oriented architecture saying, how can we do things differently? They eliminated even DRAM as a cache. So now instead of having the traditional cache architecture, you're using flash as a backend, and now you can make shortcuts, as we call it, to not have to make it certain ways. Richie has been around the block a few times, as you guys might know.
But you don't let Richie out in public.
Pardon me?
But you don't let Richie out in public.
No. He actually has some very entertaining presentations. He'll sit down, cross his legs on stage, and just sit there and talk. I love it. Anyway, so one of the brilliant minds, right? So he said, you know what? And I see that a lot of flash guys or people are taking flash and instantiating it as a cache in front of a slower tier. And the whole idea was flash as a cache, right? Accelerate the I/O, and that's fantastic until you start digging in behind the scenes and say, okay, what does that really mean? Because writes still have to make it all the way to the back drives, right? So you do accelerate the reads, but if you have a write-heavy load, you're actually not accelerating the whole lot. And what happens in what I've seen in the industry is we've taken very cheap, very large SATA drives, very small, very fast SSDs, fused it together and say, together they give you the best of the both worlds, right? Fantastic promise. The problem is, though, when the writes from the SSDs, they can be, you know, in the orders of 50 or 100,000 IOPS, hits these 10 SATA drives, they can do 75 IOPS per drive, right? It turns out the system is hugely bottlenecked on the SATA performance still, which is why we put together SAS 10K at a higher level than our competition on the same spindles with flash, and we get a balanced pieces because anything that is not on SSD in those scenarios have a huge performance impact, okay? Goes back to predictability. If you want to have a predictable performance regarding over a wide variety of I/O profiles, you need to have a solid foundation to start from. So we implemented this CEDP, as we term it, continuous with data placement architecture. And as we found when we started running the test is, well, not only does the SSD, of course, provide a lot of the performance benefits, but it actually also gives us a lot more predictable I/O patterns to the I/O that goes to disk, right? So now what happens is we're, in essence, offloading the hotspots from the disks so they can continue to do the back-end broad distribution of I/O. And that hotspot I/O pattern goes on SSDs. So we don't do caching, we do internal tiering. And internal tiering means we have data segments inside where we strategically move, based on an ROI calculation, from serving that data segment out of spindles into SSDs. And it's permanent resting place, meaning there are no write trickle effects down to the SAS drives. It continues to be served. So in essence, from that perspective, the data that ends up in SSD is served out of our SSDs just like many of the all-flash vendors serves their pieces. So the hot data, many of you know, application I/O profiles almost never are random, pure random. Pure random has been used in the storage industry for benchmarking purposes for a long time to see worst case condition. Applications work very, very differently. So the hotspots that the applications produce by having frequent access to the same data moves to SSDs.
Dave, can you go back to the prior chart for a
Sure.
second? And what's the interval between where, you know, you're almost 100% on disk to, you know, a good number of hotspot items on SSD?
Great question.
You don't have any time interval on the bottom of this.
Oh,
is that days? Is that hours? Is that minutes?
Love the question. Perfect. So
Units matter.
this was deliberately built as an up-tiering architecture. Very, very different than down-tiering. What happens in an up-tiering architecture is that you can actually make decisions much faster. A down-tiering architecture, you have a much closer tolerance on what's cold versus what's hot, and you've got to spend a lot more time figuring out what the right choice is. In an up-tiering architecture, you can actually say, every 5 seconds, I spend time understanding what up-tiering sheet candidates, so sheets is what we call those data segments. What candidates should I pick this 5 seconds? We put those in a pipeline. We evaluate the next time, okay, next 5 seconds, are they still hot? And are they of such heat index that it will pay back for me to move it? Because another problem on this is that if you're too aggressive moving stuff between tiers, you're spending I/O on the slower tier, chewing up the system performance while you're trying to accelerate. So you're actually chasing your tail.
So you're saying that interval is 5 seconds?
5 seconds. So 5 seconds.
That interval is 5 seconds?
No. What I'm saying is per
the data sample.
per sample.
I understand the data sample. I'm just trying to understand what this
How many
interval
5-second
is here.
intervals?
So usually what happens is we usually see a large portion, let's call it that, totally depends on applications, right, of hot data go into it within half an hour to an hour.
Half an hour to an hour?
Yes.
So that would...
We move 240 megabytes. We have the capability, I should say, to move the 240 megabytes every 5 seconds, right? So then it depends on how much data is hot and what gets chosen, right? So every 5 seconds, and you can do the math, and how long then of a hotspot you can cover in half an hour.
So the graphic is actually a boot storm.
This is 1,000 VDI boot storm visualized here.
So after 360 5-second intervals, it determined that it should do something about it. And
no, every 5 seconds. With a Q depth, with a pipeline.
How many 5-second intervals does something need to be hot before you guys decide to do something about it?
So it's dynamic, actually, depending on the heatness of the pieces.
So if it's
So if you
it's
are
really active, it'll get promoted faster. If it's just medium or whatever, it takes longer to.
Correct. And what happens is when you're really hot, you move every 5 seconds. After you have saturated the pipeline depth, which is less than a handful. Let's call it that for now. It depends on what the scenario goes out, but there's a dynamic pipeline as well. And the whole point here is to make smart decisions to not over-promote, to chew up I/O on the back end, but also to make sure that, you know what, you got to bob and weave with the changing user loads, because as user loads change during the day, end of month, different things, right? You got to be able to maneuver enough with those.
That's the problem with other sublun tiering solutions, is they move, if you look at compellent,
yes,
they move once a day.
Yes.
Which means if today's the end of month close, today's going to be slow and tomorrow's going to be slow because the data that was hot today isn't going to be hot tomorrow.
Yeah. Exactly.
Miserable solution.
So what happens when it's saturated? Is there any sort of caching in the
So what happens when it's
level,
saturated is that you have now utilized the SSD performance acceleration capacity. Different user applications have different hotspots, so sometimes you saturate it, sometimes you don't. But once you've saturated it, now the ROI calculations also take the I/O into consideration about moving it off. So now it comes back to comparing the coldest candidate on the SSD side with the hottest candidate on the HDD side, and will it pay off for me to swap these, right? So then it continuously moves data as it changes the I/O load. And so continuous adaptive data placement, CADP is what we call it, right? And the whole point here is that it is doing math to calculate where it's the best use of the media.
And what's the subload quantum that's moved? Did you
240 megabytes on the back end. So we're going to talk. Yeah.
So it's 240 megabytes is the amount of data you'll move in a cycle.
Correct.
What's
the page size?
What's your increment or granularity of movement?
4K, that is the increment.
64K, 240 megabytes?
240 megabytes is, so we have...
if I have a 100 kbyte index in my Oracle database,
yes,
that's getting 20% of all IOs.
Yes.
Then 239 additional megabytes of cold data will get moved into the SSD?
Correct.
Yeah. Okay.
Exactly. But what happens is, it turns out that the hotspots that we see are semi-soft. What I mean by that is that there's frequency, and this goes back to file system utilization, or to your point, indexing in databases or so, and how they go. So,
I thought I heard you said you moved 240 megabytes every 5 seconds. So you're moving effectively one data segment, hot data segment, every 5 seconds. Is that?
Yes.
That's
so we can move.
If it
They're
needs
analyzing
to be
it every 5 seconds.
So it analyzes and chooses to move or not, depending on the conditions.
One segment to move during that interval.
Correct. Correct. It moves one segment. And those segments is what we refer to as the foundational allocation grid segments. So you guys have heard us refer to matrix RAID or different type of terminology in the field. And the reason we do so is because we have a data distribution architecture we refer to as RAGs. RAID allocation GID system. It's really a virtualization layer underneath RAID. So RAID sits on top of our RAGs distribution mechanism and then collect the containers out of that. So this ICE having 40 drives can serve an arbitrary number of RAID 1 versus RAID 5 volumes on top of all the same spindles. So it's late RAID binding, if you will, when you create your volume. So you go and create a volume, say 300 gigabytes, and you can choose, do you want it RAID 1 or do you want it RAID 5?
So I think
so can we,
Ray's question was around if we have, let's say we have a pipeline full of 100 segments.
Right? Yes.
Is it going to move all matriculated 100 segments into SSD at that point in time?
No. It picks the best candidate and moves it. And then it reassesses the next 5 seconds. Has things changed enough that I need to make a different decision to move the next one?
Now,
so it's the pipeline winner that gets to go.
So can this be influenced by policy on the higher level? So other than the RAID level that influences the movement of this data for performance, can I say this application, we get into policies and real world performance?
So now you're looking at forward providing pieces, but yes. So right now, no. We're coming out with a version that's going to give us what we refer to as media affinity. So do you start an HDD and move up? Do you start an SSD and move down? Right? Do you pin a volume to an SSD? Do you pin a volume to HDD? And having those knobs can be useful in certain scenarios where, frankly, you do have infrequent accessed information that needs low latency, where an all-flash array would actually be useful, right? It would actually be useful to be able to allocate a certain segment or chunk of volume, saying, pin it on SSD, and I know I'm trading off the opportunity to accelerate other volumes, but it's my choice to do so.
Politics, layer 8 in the OSI model, it's very important.
Yes.
Yes.
This application
executives
needs high performance because the people who use it are important people.
Correct. Very much so.
Just to touch on that size of your block.
Yes.
Is that because you expect data within that same area? If there was that one hot piece that Howard was talking about, you'd expect some of the data suddenly to become hot in that section, and that's why you move such a large amount?
So the large amount is actually balanced based on the metadata and memory maps that you also need to contain to keep track of those data blocks. So there's a careful trade-off to do when you do this, because the intuitive choice for a lot of end users is the smaller you keep track of, the more efficient your architecture is. But that's many times actually counterintuitive, because what happens is...
That's flash efficiency, not CPU efficiency.
And exactly, lookup efficiency. How do you find that node in a way through a B tree to actually have a low lookup scenario? And how much memory do you need to chew up to keep those metadata tables in memory to make this not only quick, but also sustainable from a long cache perspective?
Yeah, so did you get to that value because of experience, because of measuring stuff and then reevaluating it?
So how do we get to the value? Historical reasons. As always, most of these design decisions sometimes are not necessarily thought of day one, right? So our RAGs architecture, how we allocate chunks to put them together in RAID is using this chunk size. So then the alternative is to go in and create another level of granularity chunk that you got to manage, or you leverage the one that you have. So the 240 megabytes is leveraging one that we use for allocation perspective to start with, and then we assess, is this working or is this not working? What we find with it is it's working really well.
The only reason I ask that is because imagine, pick VMware as an example, how they've moved back to the 1 megabyte block size in VMFS. Mm-hmm. So whereas they would write larger blocks, but now they're writing a lot smaller blocks, would it subterfuge your architecture where you've got quite a large block size, because now you would have a lot higher granularity at the higher level in an application than you were able to cope with? And would that really be relevant?
So, well, I guess it comes back to how did the VMFS translate file I/O to block I/O, right? Because being a block device, we see the block I/O from a VBA perspective. So now it comes back to allocation affinity of the VMFS file system too, right? And does it do a sequential allocation, and how sparse is your file system, if you will, at that point, right? Because and that changes with usage as well. So would a smaller granular chunk size give you more opportunity to, how should I put this, to stuff more hot data in flash? That's what I'm hearing from your question. And
I guess what I'm just wondering is whether the fact that a smaller block size, say it was on NTFS, that doesn't fall off, NTFS at say 4K,
right?
And you had a really, really fragmented volume where there's stuff all over the place. Would the fact that you've got only a very, very small piece that could be hot really work against your algorithm because you'd be trying to put too much into flash that really didn't need to sit there?
It's possible. I can see extreme cases where you have a flash up-tier multiplication effect, if you will, because they're spread such that you now are promoting many 240 meg blocks instead of the small ones. Yes, I mean, I can't deny that that's a theoretical possibility.
But would it take an extreme case? I guess you're saying it would take a really extreme case.
It would. We don't see this being a practical challenge today. Right. Now, what we do see that the fact that the 240 meg chunk size are very effective for us because we can also do read aggregation on the back end. So instead of doing a lot of small, because what happens when you go to a small chunk size too is that now you've got to move small pieces. And now you have multiplied the number of I/O you got to do to the low tier to up tier. So now you have an even bigger I/O hit to try to accelerate. So there's also a trade-off in going to small chunk size actually have a performance impact and penalty. Make sense?
Yeah.
So it's a balance, right? And everybody's going to argue that their size is right, of course. Yeah, right? Absolutely. That's nothing unusual. Okay. Yes, sir.
We still don't know how long that interval was on that chart.
That one there.
Samples were taken every 5 seconds.
Oh, yeah,
I don't know how many samples that is.
How long?
Count them for us?
I think we can get the axis. I don't have that here, but yeah.
Label the x-axis.
Got it. We'll get you that information. Okay.
For engineers, units are important.
Totally makes sense. So here is an attempt to visualize what's going on behind the scenes, if you will, on spindles and SSDs. So the left-hand side there is the heat map over 3 volumes on the spindles, and to the right is the heat map over 3 volumes using SSDs. So and the whole idea is x-axis is progression in time, and the redder it is, the hotter it is. So you can see the left-handmost column, if you will. So each column is a time slice. And where the red hot streaks in HDD moves over to the SSD, so you can see that at the right-hand side, the average heat index across the spindles has gone on tremendously because you've offloaded, if you will, all that performance capability into SSDs and you accelerated the HDDs as well.